So I would like to tell you about a recent result with Georg Graseger, Jan Legersky, and Josef Schicho, which is about, as Luis told us, zero-sum cycles in flexible polyhedra. So I would like to start by considering a very easy situation, I'd say. So let's consider a cycle like this one, 6 cycle, and suppose to realize it on a line. Okay, so you put so the cycle is an abstract graph, and now you draw it concretely on a line. Okay, so like here in the picture below. Then what happens is that if you follow the cycle, so you go from vertex 1 to 2 to 3 to 4 to 5 to 6 and then back to 1, and you sum the lengths of the realizations of these edges that we have, giving them, let's say, for example, positive sign if you go from left to right, and negative sign if you go from right to left. You see that the edge 1, 2 has a positive contribution, while the edge 2, 3 gives a negative one. And then so on, we add 3, 4, we subtract 4, 5, we add 5, 6, and then we subtract 6, 1. Well, if you perform these operations, you realize that you get 0. You get 0 just by telescoping, right? Because this is a telescoping sum, and every contribution cancels the previous ones. So I would like to ask you to please keep this in mind for the rest of our talk, because this will come up at the end of the talk. So I would like now to discuss a very well-known situation, which is the situation of octahedra. And in this situation, I would like somehow to connect to the previous example. So as I believe many of you know, octahedra, so the motions of octahedra have been classified already by Bricard. And there are 3 types of octahedra. This is not a partition. Some octahedra can be, or flexible octahedra, sorry, of course. Some octahedra can belong to more than just one type. So there are the line symmetric octahedra, and there are the plane symmetric octahedra, and then there are these so-called octahedra of type 3, which have the following property. So if we consider the 4 cycles in the octahedron, then what happens is that the lengths of these edges, if we sum them or subtract them in an appropriate way along one of these 4 cycles, then it gives 0 for all 3 these 4 cycles. Okay, and I would like to refer to, in this case, to Jan Legersky's very nice website, where animations are provided, and I hope you see now. So this is a type 1 octahedron, so a line symmetric. Here you see the symmetry line in black. This is a type 2. This is a plane symmetric octahedron, and then there is a type 3, so the most maybe mysterious ones. But I would like, since we have the pictures here, to focus on one aspect, namely that this condition about the sum of the lengths of the edges along one of the whole 4 cycles. Let's, for example, now look at the type 2 flexible octahedron. Well, we see that even in type 2 and in type 1, there are 0 sums of cycles, just because of the symmetry, right? The symmetry forces pairs of edges in these 4 cycles to have the same length. And then immediately it follows that if we sum or subtract accordingly the length of the edges, we get 0. Okay, so we have another somehow instance of flexible object in this case, where the sum along a cycle of edge lengths is 0. Actually, this is an example of a more general situation, namely that in general, any flexible suspension, which is essentially a double pyramid on an equator, okay, if the suspension is flexible, then Mikhaev proved in 2001 that the same condition holds, namely that there is a way to sum or subtract the edge lengths of the equator so that we get 0. So what we would like to propose is to generalize this result actually to a wider class of polyhedra, or maybe of two complexes. So in order to fix our ideas, what I would like to ask you to do for the rest of this talk is to consider a graph which is the one skeleton of a polyhedron with, in this case, this is a technical assumption, with triangular faces. We can remove this assumption later on. I mean, actually, we do it in a second part of the paper, but such an assumption makes it easier, I would say, to understand. And I would like to stress the fact that we don't have to restrict ourselves to one skeleton of polyhedra. Actually, it's enough to have weaker conditions, but I would say that for the time being, I would like to stick to this setting. So I'll just start by repeating notions that I believe are known to the community, but in order to make it clear what we mean by them. So I start with the notion of realization. So for us, realization is just a map from the vertices to R3. So it's a way to position the vertices of a graph, which for a moment is a purely combinatorial object, into the space. And then once we have a realization induces edge lengths. Okay, namely, if we if we fix an edge, then we can look at the corresponding realizations of the corresponding two vertices, and then the distance between these realizations of vertices will be our edge lengths. And what we ask is that the realization is injective, especially at least in terms of adjacent vertices. Namely, that we don't want adjacent vertices to be mapped to the same point. And then, since I would like to, so all the previous results were about flexible objects, I state the notion that we will be using of a flex. So if we have a realization rho of our fixed once for all graph, which is a one skeleton, we say that a given realization has a flex f if there is a map which is, as you see, from 0, 1 to the space of realizations. So maybe you can think about it as a path of realizations. And what we ask is that at time 0, this flex is our given realization. Then at any time, so f of t determines the same edge lengths as f0, as the given realization. And any two realizations are not isometric. Okay, any two distinct realizations are not isometric. So this, for example, this excludes trivial functions like, I take one realization and I simply translate it. Okay, this would give us a path, but this is not what we mean by flexibility. And this is the main result that I would like to sketch today. Actually, today I would like to mainly convey the technique that we adopt. So the result is the following. Suppose we have a realization that admits a flex, and suppose now focus on an edge whose dihedral angle changes during the flex. So we consider an edge where the dihedral angle is not frozen. Then what we can prove is that there is an induced cycle in the graph, and such a cycle contains the given edge, and so that the sum of the edge lengths in this cycle weighted by 1 or -1 is 0. So this generalizes the previous results. So I would like to spend a moment discussing the technique that we adopt. And the technique is a geometric and combinatorial technique, I would say. And especially as far as the geometry is concerned, I would like to point out two main aspects. The first aspect that we consider is the fact that we take R3 and we make a compactification of R3 in a particular way. I will describe it later. And what we do is to look at what happens at infinity. Okay, so this means what happens at the border of infinity. Notice that infinity does not necessarily mean what we somehow think about something very, very far. And so the infinity depends on the compactification that we choose. Okay, and we will see that we have a peculiar compactification in this case. And the second aspect that I would like to stress is that we use complex geometry, complex algebraic geometry, I would say, but the results that we obtain are purely real results, so results concerning real numbers. Okay, so even though we pass through complex geometry, we get results that hold really for real numbers. Similarly, what happens, for example, when you solve degree-free equations. Maybe you might introduce along the way some complex number, but maybe in the end you get real solutions. So I think something vaguely similar happens here as well. And please, I would like to ask you, please feel free. I don't see the chat at the moment, but feel free to interrupt me if something is not clear. So this is the compactification that we will be using. And so the compactification is a compactification of R3 into P4. Okay, so what I do is that I map a point X, Y, and Z to the point with projective coordinates X, Y, Z, and then a new coordinate, which is the sum of squares of the coordinates. So R, which is the new coordinate, is X squared plus Y squared plus Z squared. And then I have a homogenizing variable, which I call H. Okay. So you can see from the shape of a function that if we take the Zariski closure of the image of R3 under this map in P4, the Zariski closure is this quadric. It's a quadric M that has the equation x squared plus y squared plus z squared minus r times h equals to 0. So why did we choose this compactification? Maybe the main reason is that the quadric M defines as any quadric a bilinear form, which I denote here by brackets with index M. And this is a bilinear form from the underlying vector spaces of P4, so from R5 times R5 into R. I apologize for the typo. So the codomain should be R. And the main property that we use about this compactification is the following, is that it behaves very well in terms of Euclidean distance. Namely that if we have 2 points in R3, and then we take the two corresponding points in P4, for which we normalize with h coordinate equals to 0, then the square distance of the 2 points in R3 can be obtained by taking the scalar product of the points of the vectors representing the points in P4, this scalar product with respect to the quadric M. Okay, so this quadric somehow encodes a little bit the square norm of R3. So what do we do with this quadric and the bilinear form that it is associated? what we can do is that we can extend in this way the standard squared Euclidean distance to a bigger somehow portion of M, so bigger than R3 itself. So the Euclidean square distance would be in principle defined for any pair in M times M coming from a pair of points in R3. What happens is if we use this formalism given by the bilinear form, we see that the Euclidean square distance extends to a rational function which is defined on a bigger subset, not just R3 but on a bigger subset. It's not defined on the whole M times N, but on a bigger subset. And there is a very easy geometric way of describing at which pairs this function d is not defined. And it's not defined when one of the points sits at infinity, so does not belong to R3. You see, it has h equals to 0, which is what points from R3 can never have, because they always have h different from 0. And then the second point should lie on the tangent space of the first point along this at this quadric. So this is what is called the embedded projective tangent plane of the quadric at the point Q1, for example. Or you can have the completely symmetric condition. Okay, so if a pair does not satisfy these two conditions, the function d is defined. What do we do now? Well, let's investigate a little more how this compactification M looks like. So M is constituted of R3, and then what we can call the boundary or infinity, which is what I denoted here by M infinity, namely the intersection of M with the hyperplane H equals to 0. So this is constituted of points which do not come from R3. So if we look at the equation is now x squared plus y squared plus z squared equals to 0. The r is missing, the h is 0. So this means that since a variable is missing, this object is a cone, and it's a cone over a plane curve. What's maybe funny about this cone is that this cone has essentially a single real point, namely the vertex of this cone, which is the point 0, 0, 0, 1, 0. But it has no other real point. So since what we want to do is to use effectively this boundary, this infinity, what we do is from now on, we will extend everything we have done so far to the complex numbers. Okay, and since we define everything in terms of equations, all the notions that we defined so far make sense. Okay, M infinity, the bilinear form, they all make sense over C. And I would like now to tell you what is the main technical result that we will be using. So the main technical result is the following, is that if we pick a point which lies at infinity, and we define this set of, let's say, finite points of P, fin P, which is defined as the tangent space at P, intersected with M and intersecting where H is not 0, then what happens is that whenever we restrict our extended distance function to any of these sets, like fin P, our distance function behaves like a square distance on a line, on a one-dimensional subset, on a one-dimensional line, really linear set. Okay, as you see from the formula that you have below, so the distance is given by, so there's this function pi, which I will not specify further because it's not really not needed. But what's enough to do is that to map Q1 and Q2, any 2 points under this map pi, and then take their difference in R or in C, if we extend to the complex numbers. And this is the shape of the distance function whenever we restrict to these funny objects, which we denoted by fin P. And so whenever we have, whenever we see this behavior, then we can set up a goal. Well, suppose that in any way, which I mean, in a way which might be a bit mysterious at the moment, we manage to find a realization of our polyhedron for which a whole cycle passing through the vertex whose dihedral angle changes, so sorry, the edge whose dihedral angle changes, namely the edge we are interested in. So suppose there is such a realization where this whole cycle lies on a set of a form this thing P. Then, from the very first example that we saw at the beginning of this talk, we know that we proved our statement. Why? Because if the whole cycle lies on such a thin P, then on thin P the distance d behaves like a one-dimensional distance, and in one dimension, if I have a cycle and I sum around the cycle, I get 0. Okay, so our new goal is to find such a strange realization of our polyhedron. So you see, it's a strange realization because it involves. So in principle, it need not to involve this point P, which lies at infinity, but actually it will. And so it's not a realization in the standard sense. So we cannot see such a realization, but it's enough that it exists so that we can conclude our statement. And this is what I meant by using the complex geometry. So the extending to the complex numbers will allow us to prove the existence of such a realization. But for us, it's just enough the existence, because then all our edges have a real length, and then the property of summing up to 0 doesn't matter whether it's a property that it's proven for the complex and it's instantiated over a specific real example, which is the one we start from. So how do we find such a realization? What we do is that we need to consider what I would call configuration spaces of the polyhedron. So once we have the realization that admits a flex, what we do is that we define this set W of all realizations inducing the same edge lengths of a given one. And I can say that this is in C to the third because you can write these conditions down in terms of polynomials, and so they make sense of the very complex numbers. We immediately see that this set W is very redundant, because whenever we have one realization on such a W, any isometric realization will also lie on W. So what we want is that we stop this action by isometries, and to do that, we freeze the isometries by freezing a triangle. And the triangle that we take, for example, this triangle W1, W2, N. So we have these two adjacent vertices of a given edge will be called N and S for maybe, for example, north and south pole. For example, this is what happens in suspensions. You have an equator and a north and a south pole. So, and then we define Z. So Z now can be embedded. So Z was a subset in C to the third to the V as W. And now C to the third can be embedded in M. So C to the third to the V can be embedded in M to the V. And the fact that we have a flex means that Z has, Y is the Z closure of this image. And the fact that we have a flex, namely we have infinitely many points on Y, means that Y has positive dimension. Now, not only that, since we suppose that the angle at this edge Y1, W1, W2 is not frozen, then if we look at only what the vertex S does, we see that the vertex S moves, right? So traces at least a curve. So then if we take this Y, this set of configurations, and we project on the, say, coordinate, in quotes, corresponding to the vertex S, what we know is that the image of this map is positive dimensional as well. Okay, and then what happens is that, so this little cube is, say, our M, our compactification of R3, and this white curve is the projection of our set of configurations Y into the coordinate related to the vertex S. Since this projection has positive dimension, there's eventually, since M is compact, this projection must intersect the boundary, what we called M infinity. Okay, so this means that there exists in our Y, in our set of configurations, a special completely complex realization, we call it rho infinity, such that the realizations of the vertex S is at infinity, is in M infinity. So what do we do with this? Well, using this very special realization, we define a coloring of the vertices of our graph, of our one skeleton. How do we color the vertices? Well, we color them in three colors, red, blue, and gold. The only important colors are the red and the blue. The gold is just because will not matter later. I mean, it's a possibility that can happen, but it will not matter. So we color by red those vertices which are sent to, let's say, true points, namely points not at infinity in this realization rho infinity. So a vertex V is colored red if rho infinity of V is not at infinity. While it's colored blue if it is at infinity and it has a technical property which I will not explain in detail, but so essentially the point is that infinity is a cone over a curve, over a plane curve, and we have a particular point which is this rho infinity of S, which we know to be at infinity. Then this rho infinity of S can be projected to this plane curve, and we can do the same with rho infinity of V for any vertex V which is also at infinity. And if the 2 points project to the same point on the plane curve, then we color this vertex in blue. This is a technical construction. The reason why we construct it like this is that using the properties of the extended distance that we introduced before, we can prove the following. So we can prove that in our graph there exist 2 cycles. A first cycle is constituted of vertices that are red, namely they correspond to finite points not at infinity. And this cycle of red vertices contains the 2 vertices W1 and W2. And then there is a cycle of blue vertices, which contains the vertex S. Now, the properties of our extended function D allow us to prove that what actually happens for the vertices in the blue cycle is that they are all sent by this strange realization to the same point as rho infinity of S. So all those points are somehow contracted to one point at infinity. But the nice thing about the red vertices is that they are all sent to the corresponding thin space, the point of finite, the set of finite points corresponding to rho infinity of S. Okay, so if you remember what we said before, now I will summarize it. Essentially, this closes our proof. Why? Because what we did was we started from a realization that admitted a flex, and we found a very strange realization rho infinity, such that there is a whole cycle containing our edge W1, W2 that lies on a set of a form thin P. Now, since this realization rho infinity is defined in purely polynomial equations, so using purely polynomial equations and Zariski closures, the lengths of the edges that we started from in rho, which are contained in this thin P, are the same also for rho infinity. Okay, this is why, because the definition we took of first W, then Z, then Y, and hence rho infinity, which was found in Y. Now we have a whole cycle that lies on such a set, such this set thin P, where we proved in the key technical lemma that the distance behaves like a one-dimensional distance. But then this means that if we sum up weighting in a suitable way the edge lengths of this cycle, then we get 0. And this hence proves the result we wanted to show. And then, since this is a very beautiful, very interesting workshop about open problems, let me finish my presentation, and maybe if you have any question, I would be gladly try to answer them by proposing a few open questions. So the first one is, actually this is something that moved us at first in order to prove this statement. Can this kind of necessary conditions for flexibility allow us to classify motions of polyhedra that are more difficult than octahedra? And then, since this compactification seems to work reasonably well with the Euclidean distance, I wonder whether we can use the same compactification in order to study other problems that involve distances. And third, whether we can find, maybe for other questions in rigidity or flexibility, other compactifications that encode some interesting properties, maybe about angles or other things that we care for rigidity or flexibility, and use maybe a similar approach. So, okay, this is what I wanted to try to tell you. Let me say this: the properties that I stated follow from both the properties of a function D and some combinatorial arguments that you do on this graph. But the two are intertwined, and what I just wanted to say is that they are a little bit technical, but each of them, I would say, is reasonably simple in its own. So if you have, in case, questions about each of them, I'm glad to try to answer them, and I can also refer you them later to the paper. Thank you very much. Thank you.
And thank you, Matteo. That's really a very nice talk and quite fascinating results. So, as usual, I'll throw this open. So if you have any questions, feel free to shout them out, raise your hand in Zoom, type them in the chat.
Yes, I have a comment. You know, years ago, I essentially classified the flexible suspensions. This is what you talked about before. And it's actually, I tried to publish some of the results, but they couldn't find a referee. So it still exists on some papers in my webpage. The thing is that when you look at a suspension, you look at the distance between the North and the South Pole, and then you write the condition. Well, essentially, you write what the projection of these sideways pairs of triangles, as you said, that projection onto the North-South axis. is an angle. You take the exponential of that angle, and you think of that as a complex product of terms. And each of those terms is a ratio where the numerator of the ratio is a rational function plus a square root. And what happens is that the product of these terms is 0. So that's a condition for the thing to close up and the thing to be flexible. And then from that information, you can get things like you can get that the sum of the volume of the whole object as it moves is 0, not just constant, 0. So it seems like your angle, your alternating sum should follow from that, because it's a, I don't know, I wouldn't say it's absolutely complete, but it's a fairly complete characterization of flexible suspensions, namely the suspensions where the north and south axis go together. So things that you're saying about that would, things that you're saying about what these things look like are like that. In particular, the third octahedra, or the Bricard octahedra. Is that true, or is that, have you looked at that?
I have to say I haven't. I wouldn't be able to answer your question. Thanks, first of all, thanks. I haven't looked too much into suspensions. So
I thought you wrote that in the beginning. You wrote a suspension in your first talk.
Yes, but so we knew that the same happens. So the same happens for suspensions, but I haven't studied the motions of suspensions. So what I wanted to say by this is that this property of summing up to 0 was known for suspensions.
Oh, I see.
Then we wanted to prove it for more general objects.
I see. So suspensions are a natural thing. So I looked at suspensions, and I wanted to have more involved polyhedra, but I didn't see how to do it. But it's a sort of a nice thing. You look at the suspension, and you get the product of these terms. And what happens is that the products, they look like the product of whole numbers. They cancel various terms of the product. This is a complex number now. The real part is the rational part, and the complex part has a square root. And the product of those terms has to cancel, and there's a branch point, and you run around the branch point, and you get rid of some of the terms. So you get some cancellations of that sort. And I was never able to get anything more complicated than suspensions. So I don't know, can you get other information like the volume of the polyhedron as it flexes and things like that?
No, not at the moment. So what we really were after was to generalize, to provide one necessary condition for the flexibility of a wider family of two complexes. Namely, if we have a two complex in which for any edge you have exactly two faces adjacent to that, then our theorem applies. And it means that if that object flexes, has a flex, then for any edge which is not frozen, there will be a cycle in which the sum of the edge lengths is 0.
But what happens if part of the polytope is fixed, it's rigid, that some dihedral angle doesn't change?
Then, as far as this result, we cannot say anything about that part.
So in other words, you have some of these things that add up to 0, but you don't include edges that are fixed, where the dihedral angle is fixed. Is that right?
Yes. Yes.
Oh, that's interesting. Because I was convinced that this business that when you have a flexible polyhedron, the volume is constant. Yeah, that's great. But I was convinced that it should be that the volume is 0, and so it can't be embedded. That was the ultimate goal, to show that the thing isn't embedded. And if the volume were 0, where it flexed, that would do it. So if it's true that, so you can include an angle, you can include an edge in your thing if the dihedral angle moves during the flex. Is that right?
Let me, yes, because it should be true. I don't want to say, let me think for a moment to your question. Yes, but yes, I think so, sorry. Because sorry. I wanted to. No, it's not written here.
But couldn't some angle move over here that's tied to another angle over there?
So
That's
I
sort of
hate
what's
to,
happened. That happens with the suspension, that there are two that are, I think, groups of 4, they're all tied together.